Section 7.4, rank theorem. In this section, we study the relationship between the rank of A and the theorems that related to the dimensions of subspaces associated to the matrix. Okay? First, rank theorem, 7.4.1. For any matrix A, the dimension of row space of A is same as dimension of column space of A. Okay? Actually, yeah, you learned the dimension of the column length and rows lengths are same. Actually you checked it. But here I gave a rigorous proof for that. We have seen there exists an invertible matrix, invertible n by n matrix Q and an invertible n by n matrix P such that Q inverse AP has this form. Q inverse has identity matrix and 0 and 0 and 0. We saw it in the early part of section 7.3. So there exists a non-singular matrix P and Q that makes Q inverse AP is A1, which has this form, where I is the R by R identity matrix for some R. And this R is going to be the rank of the matrix A. And the rest of the matrix is zeros, all zeros. For this matrix, it is obvious that the row rank of this matrix and column rank of this matrix are same as R, isn't it? There are R linear independent rows and R linear independent columns. So the row lengths and column lengths are both R. Okay? The strategy to reduce an arbitrary matrix to this form can be found in this web address at MIT. And this is a kind of special form of Sylvester's law of inertia. But this is not difficult. But yeah, you will see it. But in here I mentioned this. So from this observation, we see the row lengths and column lengths are same. Okay. Next. For rank of A, it is the rank of A is less than or equal to the size of the row and the number of columns. So it's less than or equal to minimum of M and N, isn't it? Because the row length is less than the number of rows, and column length, the number of linear independent rows, is less than or equal to the whole number of the columns, isn't it? So the rank of A should be less than the number of rows and the number of columns. So it should be less than or equal to minimum of M and N. Okay, that's this story. The dimension of row of A is less than N. Dimension of column space of A is less than N. So those should be rank of A should be less than or equal to M and N. Next, rank theorem 3. For an n by n matrix A, the following hold. The dimension of row space of A plus dimension of null space of A is the same as the number of the columns of A. Number of columns of A. That means rank of A plus nullity of A is equal to N for this matrix. Similarly, we think about the A transpose. A transpose is what? It's an n by m matrix. A transpose is an n by m matrix. So the dimension of row space of A transpose plus the dimension of null space of A transpose should be the number of columns of A transpose, isn't it? So that can be written as a dimension of column space of A plus dimension of null space of A transpose is equal to the number of rows of A, which is the same as the number of columns of A transpose. So this can be written in this way. Rank of A plus nullity of A transpose is equal to M, because A transpose has size n by m. So the number of columns in A transpose is m. Yeah. And then theorem 7.4.4. For a square matrix A of order n, A is invertible if and only if rank of A is equal to n. Okay? This is also very useful theorem. If A is invertible, then AX has what? Has a solution. Only one solution, which is a zero vector. So AX equal 0 has the trivial solution only. So what's the null space of A? Only zero vector. Okay? So what's the nullity of A? What's the dimension of this null space? That's 0. There is no linear independent vectors in it. So the dimension is 0. Okay? So by rank nullity theorem, what is it? Rank of A plus nullity of A is equal to n. But nullity of A is equal to 0. So rank of A should be n, which means A is an invertible matrix. A square matrix, A is an invertible matrix. Okay? This can be reversed. Similarly, if rank of A is equal to A, then by rank nullity theorem, rank nullity of A should be 0. Then null space of A is only a 0 vector. So AX is equal to has only trivial solution. So A should be invertible. So vice versa. Okay? Find the rank and nullity of the following matrix. If suppose we have a matrix like this, then by using Gaussian elimination, then we can find that REF of A, Gaussian elimination. This is REF of A. What's the rank of this matrix? 1, 2, 3. There's three leading ones. So the nullity of this matrix is 4 minus 3. So nullity of A is equal to 4 minus 3, which is 1. Okay. You can define a matrix A, and you can find the rank and nullity in this way, which says your computation was right. Rank is 3, nullity is 1. Okay. And for theorem 5, for matrix AB with multiplication AB defined, the following hold. Null space of B is a subset of null space of AB. Null space of A transpose is a subspace of null space of AB transpose, and column space of AB is a subset of column of subspace of A. Row space of AB is a subset of row space of B. How can we show this inclusion? Set inclusion. All we have to do is just to choose an arbitrary element from one side and show it belongs to the other side. That means every element, every vectors in one set belongs to the other one. That means this set is a subset of this. Isn't it? So here, we prove the first one first. Choose arbitrarily vector x from the null space of B here. Then what it says? Bx is equal to 0 because x is in the null space of B. Then, and multiply A on both sides. Then ABX should be 0 as well. Isn't it? But this also can be written as A times BX. But BX is 0 always. So AB is equal to 0. A times 0 vector is a 0 vector. So what this means is X is in the null space of AB. So X is in the null space of AB. This implies arbitrary vector in null space of B belongs to null space of AB. So this says null space of B is a subset of null space of AB. Okay? Every other thing can be similarly. Others can be shown similarly. Choose just arbitrarily vector from here. Show it belongs to the right-hand side. Rank of AB is less than or equal to minimum of rank of A and minimum and rank of B. Yeah, this comes directly from here. Rank of AB is less than rank. This is subset of this one, this side, row space of A. So rank of AB is less than rank of B, and rank of AB is less than rank of A. Okay. Okay. Next. Multiplying a matrix B by an invertible matrix A does not change the rank of B, which means if determinant of A is not 0, then rank of AB is same as rank of B and rank of BA. It also follows from the theorem 7.4.6. For a given matrix, if we multiply an invertible matrix, does not change the rank of the matrix. Okay. Theorem 8. Suppose A has a rank R. Suppose an n by n matrix A has rank R, then every submatrix C of A satisfies this. Rank of C is less than or equal to the rank of A. So the rank of a submatrix cannot exceed the rank of the full matrix. Second, matrix A must have at least one R by R submatrix whose rank is equal to R. Okay, these are two facts. So suppose you have a matrix whose rank is R. Then you can choose a linear independent rows and linear independent columns and form a R by R submatrix. Then it is whose rank is R, isn't it? That's the second part. Okay, here is the proof. The rigorous proof here. Suppose the submatrix of C is obtained by taking S rows and T columns of A. Okay? Then just choose a submatrix, just choose S rows and T columns from a given matrix. Then then we have S by T submatrix C. Then row space of C is a subspace of row space of A. So rank of C cannot exceed the rank of A, isn't it? Okay. So rank of C is equal to dimension of row space of C, which is less than or equal to the dimension of row space of A, which is same as rank of A, which is R. So rank of C cannot exceed the R. Okay. Second part is suppose rank of A is R, then there are R linear independent rows of A, then choose, then the matrix B consisting of R linear independent rows has rank equals to R. And now we form a matrix C by taking R linear independent columns of B, then C is an R by R submatrix of A whose rank is equal to R. So we just choose linear independent rows and columns to form a C by R matrix whose rank is R. This is the last theorem of chapter 4, invertible matrix theorem. Here, for an n by n matrix A, the following are equivalent. Here, we start from A is invertible. The determinant of A is not zero. A is equivalent to the identity matrix. A is a product of elementary matrices, and A has a unique LDU factorization. We skipped the proof here of that. And the second 6, 7, 8, 9, and rank of A is equal to n. The row vectors are linear independent, and row vector spans are n, and TA is 1 to 1, TA is 1 to, and lambda is equal to 0 is not an eigenvalue of A, which was a problem from the midterm examination, and nullity of A is equal to 0. They are all equivalent. Now we have how many? We have 18 equivalent statements for the invertible matrix. Here we may define a left inverse and right inverse. This is not the scope of this introductory linear algebra class, but this is also belongs to this equivalent statement. Here is the proof. Okay, so the way of proving this equivalent statement is making a cycle that show. So I did choose the cycle like this. So we were able to show this 18 statements are equivalent. You may take a look and try to show a couple. And if you find any questions, then feel free to ask it in Q&A. I'll be happy to answer on those. I think that's the end of section 7.5 and 7.4. Then we will continue the section 7.5 projection sharing. Any questions?